then you guys know, you just told me, acceleration is minus 9.8, where g is minus 9.8. We call it minus because it's accelerating down, and up was taken to be the positive direction. In that case, y of t will be minus 1/2 gt squared plus c plus bt. So the point is, every object falling under gravity is given by the same formula, but there are many, many objects that can have many histories, all falling under gravity. And what's different from one object and the other object is, when was it dropped, from what height, and with what initial speed. That's what these numbers are going to tell us, and we can verify that as follows. If you want to know what the number c is, you say, let's put time t equal to 0. In fact, let me go back to this equation here. If you put time t equal to 0, x at 0, it doesn't have this term, it doesn't have this term, and it is c. So I realize that the constant c is the initial location of the object. And it's very common to denote that by x naught. So the meaning of the constant is, where was the object at the initial time? It could have been anywhere. Simply knowing the acceleration is not enough to tell you where it was at the initial time. You get to pick where it was at the initial time. Then, to find the meaning of b, we take one derivative of this, dx dt. That's velocity as a function of time. And if you took the derivative of this guy, you will find it's at plus b. That's the velocity of the object. Then you can then understand that v of 0 is what b is, which we write as v0. Okay, so the final answer is that x of t looks like x naught plus v naught t plus 1/2 at squared. Okay, so what I'm saying here is we are specializing to a limited class of motion where the particle has a definite acceleration a. Then in every situation where the body has an acceleration a, the location has to have this form, where this number is where it was initially. This was the initial velocity of the object. So when I threw that thing up and you caught it, what you were doing mentally was immediately figuring out where it started and at what speed. That was your initial data. Then, in your mind, without realizing it, you found the trajectory at all future times. Now, there is one other celebrated formula that goes with this. I'm going to find that. Then I'll give you an example. Now, I'm fully aware that this is not the flashiest example in physics, but I'm not worried about that right now. You'll see enough things that will confound you. But right now, I want to demonstrate a simple paradigm of what it means to know the present and what it means to say this is what the future behavior will be. If we want to do that in the simplest context, then we can make the example more and more complicated, but the phenomenon will be the same. So what we have found out so far, I'm purposely going from x to y because I want you to know that the unknown variable can be called an x or can be called a y. It doesn't matter. As long as the second derivative is a, that's the answer. Now, that's the second formula one derives from this. You guys probably know that too from your days at the daycare. But I want to derive that formula and put it up. Then we'll see how to use them. Second formula tries to relate the final velocity at some time t to the initial velocity and the distance traveled with no reference to time. So the trick is to eliminate time from this equation. So let's see how we can eliminate time. You know that if you took a derivative of this, you'll find v of t is v0 plus at. What that means is, if you know the velocity at a given time and you know the initial velocity, you know what time it is. The time, in fact, is v minus v0 over a. If I don't show you any arguments for v, it means v at time t. And the subscript 0 means v of 0. So what this says is, you can measure time by having your own clock. The clock tells you what time it is. But you can also say what time it is by seeing how fast the particle is moving. Because you know it started with some speed. It's gaining speed at some rate, A. So if the speed was so and so now, then the time had to be this. So the time can be indirectly inferred from these quantities. Then you take that formula here, and you put it here. Wherever you see a time t, you put this expression. So what will you get? You'll get an expression in which there is no t. T has been banished in favor of this. So I'm not going to waste your time by asking what happens if you put it in. I will just tell you what happens. What happens is you will find that v square is equal to v0 square plus 2a times x minus x0. How many people have seen this thing before? Okay, that's a lot. Look, I know you've seen this. At the moment, I have to go through some of the more standard material before we go to the more non-standard material. If this part's very easy for you, there's not much I can do right now. So let me draw a box, because drawing a box to you guys means important. So these are the two important things. I claim now, remember, I want you to understand one thing. How much of this should you memorize? Suppose you've never seen this in high school. How much are you supposed to memorize? I would say keep that to a minimum. Because what the first formula tells you should be so intuitive that you don't have to cram this. We're talking about particles of constant acceleration. That means when I take two derivatives, I want to get a. Then you should know enough calculus to know it has to be something like at squared. And the half comes from taking two derivatives. The other two you know are stuff you can add. And you know why you're adding those things. Because the particle has a head start. It's got an initial position, even at t equal to 0. And it has an initial velocity. So even without any acceleration, it will be moving from y0 to y0 plus vt. The acceleration gives you an extra stuff, quadratic in time. Once you got that, one derivative will give you the velocity. Then in a crunch, you can eliminate t and put it into this formula. But most people end up memorizing these two because you use it so many times. Eventually it sticks in you, but you shouldn't try to memorize everything. So we are now going to do one standard problem where we will convince ourselves we can apply these formulas and predict the future given the present. So the problem I want to do, there are many things you could do, but I just picked one. This is the one with round numbers, so I can do it without a calculator. So here's the problem. There is this building, and it's going to be 15 meters high. And I'm going to throw something, and it's going to go up and come down. The something I throw up has an initial speed of 10 meters per second. So we have to ask now that my claim is, you can ask me any question you want about this particle, and I can answer you. You can ask me where it will be 9 seconds from now, 8 seconds from now, how fast will it be moving. I can answer anything at all. But what I needed to do this problem was to find these two unknowns. So you got to get used to the notion of what will be given in general and what is tailor-made to the occasion. So we know in this example